Good morning, everyone. My name is Josh White, and I'm here representing the NRAP Induced Seismicity Working Group. And we wanted to give you a brief update regarding some of the tools we've been developing for induced seismicity management. So our approach within the Induced Seismicity Working Group has really centered on two elements. One is we wanted to put together some guidance documents, really basically recommended practices for how we see induced seismicity risks could be managed at a storage site, some recommendations for monitoring and so forth. Denise Templeton is going to give a very detailed discussion of that recommended practices document this afternoon, so I highly encourage you to attend her talk. In parallel to that guidance, though, we've also been trying to provide supporting tools that can help you carry out certain elements of those recommended practices. And so that includes things like the short-term seismic forecasting tool, or STSF, the risk-CAT tool, the state of stress assessment tool, SOSAT, and things like the fault leakage ROM that could be used within the integrated assessment model. So in this talk, I'm going to focus on the STSF tool and give a brief introduction, as well as risk-CAT. SOSAT and the fault leakage tool will actually be described in later presentations today. So if you're not familiar, the short-term seismic forecasting tool was really developed with the idea of improving current stoplight management techniques. So at many carbon storage sites, they will often implement what's called a stoplight, with the idea that if observed seismicity is below a certain threshold, you're in a green light scenario and you can continue to operate as expected. Above a certain threshold, you may enter into an amber light scenario where you have to modify injection, potentially collect additional data, and so forth. And then if you trigger a sufficient magnitude earthquake, you may end up in a red scenario where you need to halt injections and dramatically rethink the operation. So this is a very good management strategy, but it only relies on individual earthquakes, and it's not particularly proactive. It's a completely reactive system. And so what we've been working on within the group are basically short-term seismic forecasting methods. So obviously we can't predict individual earthquakes, but we can sort of understand the statistics of seismicity that's being observed and sort of make estimates whether the statistics are indicating that a site is at an unusually high hazard level that may suggest you should move into sort of an amber light scenario or possibly a red light scenario. And so our first step at this was the short-term seismic forecasting tool. This was released a few years ago, and we've updated it recently based on user feedback. And it's available right now on the EDX website with user manual and test cases and so forth. So the current short-term seismic forecasting tool relies on a particular statistical model, which is called an epidemic type aftershock sequence. This is a model that's frequently used in natural seismic analysis to really understand how aftershock sequences behave. And the idea is that earthquakes can often be treated as a cascade, where, for example, a large magnitude event may cause stress changes that trigger, other smaller magnitude events in this case, and those events themselves could potentially trigger sub-events. Those sub-events may have larger magnitude and so forth. And so we think of the total rate of earthquakes as consisting of some background rate, and then plus some triggered rate. And the events at later times, their rate will be dependent on events at earlier times. And this does a very good job at sort of describing natural seismic sequences. The element we've added here, though, is to include the fluid injection as a modification to the background rate, as a modification to this lambda 0 term. And so we consider the background rate as consisting of a true natural background rate, and then some rate that is somehow a scaled function of either the pressure that the reservoir is experiencing or as a proxy the injection rate. So this is a very simple model, but then given an earthquake catalog and an injection rate, we fit the parameters of these models using, let's say, historically observed seismicity. And then we forecast forward into some forecast window, which is typically quite short, usually on the order of a few days or weeks. Um, and so to give you one example of this, this is a case study we performed for Paradox Valley, which is a large-scale brine disposal site in Colorado. And so in the three panels here, you can see actually the injection rate, the actual observed seismic frequency, so number of events over a 5-day period is the normalization. So you can see the data here. You can see, for example, that when injection rate was relatively high, there was more earthquakes. They then reduced injection rate, and they were able to sort of reduce the frequency of earthquakes, but we still do see occasional clusters of seismicity. And then this would actually be the ETAS prediction. So again, using prior to a certain date, all of the observed seismicity, and then predicting forward in a 5-day window. And so it's not a perfect match to the observed seismicity, but it does a reasonably good job of mimicking the statistics of what we're seeing. So we developed the short-term seismic forecasting tool several years ago, and it's been available. But we recognize that it has a few flaws, a few features that we would like to add. And so more recently, we've been working on an updated version of this same basic concept. And we're giving the tool a new name, which we're calling Orion. And this new tool has three basic elements, three basic improvements. The first is that we wanted to make the tool Python-based. This is consistent with the integrated assessment model. Python provides a very flexible framework for both providing a GUI interface and allowing advanced users to interact directly with the modules in the code. And so we've sort of started rebuilding the structure of this seismic forecasting tool within a Python-based framework. The second element of this is we're actually moving from a single model, which was this ETAS model that we described, to actually providing ensemble forecasts. And so the basic idea here is that given some observed earthquake catalog, we actually want to apply a variety of different forecasting models. So we have, a particular version of the ETAS model here, maybe a second version. We've been working on some rate and state type models. In the absence of information, we might use a very simplistic sort of background hazard model from OpenSHA, which is a publicly available seismic hazard tool. And so each of these methods uses a very different model, a very different way of predicting future seismic frequency. But then what we can do is we can actually weight these predictions based on the quality of the prediction with observed data. And so those models that are actually outperforming other models will over time be weighted more highly. And so we end up not with a single forecast, but actually an ensemble weighted forecast of models. And this type of methodology is used frequently in many other domains, weather forecasting, climate forecasting, and so forth. And it's a good way to ensure that any flaws that exist in individual models aren't overly weighted, and that, in fact, by having this ensemble of models, we're able to account for different features in the response space. And then the last thing we want to add is a more direct connection to this idea of a stoplight management scheme. So in the previous tool, it would give you a prediction of seismic frequency, but we think we can take that a little bit further and go from hazard all the way through to sort of an assessment of risk, and then based on certain thresholds, an indication of, let's say, whether or not you're in a green light scenario, an amber light scenario, or a red light scenario. Another tool that we've been working on for many years is RiskCat. And so this is the framework for doing a complete induced seismicity probabilistic seismic risk assessment. And so this would be very much sort of the counterpart of the integrated assessment model for the induced seismicity perspective. And so the basic idea here is that you have to provide a seismicity catalog. So that might be recorded seismicity observed at a site. It may be simulated seismicity, for example, using some of the earthquake modeling tools that have been developed here and elsewhere. It may be some hybrid of that. And so that seismicity catalog basically provides the one element of the hazard. Another element, though, is then ground motion. So given an earthquake of a certain magnitude at a certain depth and in a certain region, we need to be able to predict what sort of ground motion we may expect at the surface. Because ultimately, people don't care about earthquake magnitude, they care about ground motion. And so this RISCAT tool provides a variety of ways of doing ground motion prediction. So this includes empirical ground motion prediction equations, various analytical functions, and then also the ability to do numerical modeling. Together, the expected seismicity and then the resulting ground motion, that actually provides what we call your hazard. And then when you combine the hazard with fragility, and what fragility means basically is the likelihood of observing damage given a certain ground motion. This is easy to visualize in the case of a building. Buildings are built to a certain structural code. And so given certain ground motions, we can predict what fraction of buildings might experience minimal damage or severe damage and so forth. But you can actually apply the same concept to people, so ground motions below a certain level are undetectable by humans, whereas above a certain level that may sort of annoy people, and then very large ground motions can obviously scare people and so forth. And so convolving the hazard with the fragility gives us risk. And so to see what this looks like for an individual site, this is a synthetic calculation, but you can see that we've computed mean hazard, which is basically given as the annual probability of exceeding a certain ground motion acceleration, okay? And so the red, yellow, and green, green, blue, and red lines here represent different sites, different distances away from a certain carbon storage system. And you can see we have a background hazard in the dashed line, and then a enhanced hazard that may be associated with induced events at the site. And again, using this hazard, we can convolve it with our fragility to come up with a nuisance potential. So think of this as the fraction of the population who might be annoyed or concerned by seismicity being generated at your site. And again, there is a background curve associated with natural seismicity at the site, and then some elevation and seismic risk that might be associated with triggering earthquakes. Now, the RISCAT tool is a little different from some of the other tools being made available through the NRAP partnership. It is a little bit more difficult to use. It requires fairly significant expertise in seismic hazard and seismic risk forecasting. So we're making it available as a beta version. We're putting it in the public domain, particularly for other researchers and seismologists and consulting firms who have this sort of expertise and are really interested in understanding this sort of seismic workflow. Others may find it a little bit difficult to use, and we know that. We're working right now on improving the manual and the interface generally. But for the moment, we're keeping this as a beta product. And with that, there's a very brief update on our status. If you have any questions whatsoever about the tools or the efforts within the seismicity working group, please contact either myself, Josh White here is my email, or Corinne Bachman. She's the lead developer for currently both for the short-term seismic forecasting tool and RISCAT. And so both of us are a good resource for any questions, and we welcome comments and suggestions as well. Thanks very much.